started. I'll have your exams back to you next time. I've graded almost everything. And I'll put this delicately. You guys did not exactly cover yourselves with glory. Okay? So let me get the exam, and I will email out, of course, as usual, solutions and whatnot. When you see the solutions, try to figure out, what you missed and why. And just be aware that, just like the situation we had in Chem 272, this material builds on itself. And so if you miss something, it's not as if, okay, next exam we can, some new material and forget about it. You really do have to make sure the stuff makes sense. So figure out, a lot of people, I think, missed the first problem, which, it was the same, it was just a minor variation of one of the ones that was in the book. The book had the 1-methoxynaphthalene, this was 2-methoxy. And it's okay if you make a mistake, that's okay, but I think what should trouble you is a lot of people didn't know where to start, and that's not good. On the other hand, the spectroscopy problem, which I thought was going to be the hard one, a lot of people nailed that, so that's good. Spectroscopy, a lot of people have figured out the ones where it showed getting Mach spectrum. So I thought that was going to be the really hard problem, but actually that was not the case. Anyway, you'll get your solutions back through Laulima, and I'll have the graded papers for you I think in a week. So now let's pick up where we left off in chapter 18. Chapter 18 is where we learn something about transition metal metallic chemistry. And so this is a growth area. It's an area that kind of crosses the boundaries of organic chemistry, catalysis, and also a lot of biology. A lot of the enzymes that our bodies use have at their active site a metal, something you've seen before. And so you don't need to memorize the periodic table. The periodic table will be available to you, but just recognize that the number of valence electrons in neutral metal, of course, follows this period. And again, you don't have to memorize any of this, but you should know how to figure it out just by looking at the periodic table. Okay, so what makes this chemistry a lot more complicated than what we've seen is that you have more electrons. And so you don't have an 8-electron rule anymore, no octet rule. Here you have an 18-electron rule. And so a lot of the complexes that we're going to see, a lot of these organometallic compounds, are going to be 18-electron or 16-electron compounds. The first organometallic reaction that we talked about just briefly last lecture was this one, the Heck reaction. I mentioned that Richard Heck received the Nobel Prize, shared the Nobel Prize with Suzuki and Negishi through, there's a Negishi reaction and a Suzuki reaction. We'll talk about both of those. This is it looks magical, really. I mean, you have an aryl bromide and you have ethylene, and you form this red bond to the ethylene, and this is completely unfunctionalized. And so it looks as if what you're doing is that you're somehow doing a displacement of HBr, and the yield is very good. Now, the key, of course, is the metal, palladium. And so this process absolutely will not proceed in the absence of palladium. But in the presence of even a small amount of palladium, you get a catalytic process. The palladium is not consumed, and you end up getting this alkylation of an aromatic. So remember that what ties this chapter together with everything else is that it's a way of making typically carbon-carbon bonds with aromatic rings. Now, it turns out this chemistry can be applied to carbon-nitrogen, carbon-oxygen, carbon-sulfur, and many others. We're not going to talk about that aspect. So this is not an SN1 reaction. It's not an SN2. It's not a nucleophilic aromatic substitution. It's none of those things. This is a completely different mechanism, and it is catalyzed by transition metal. Okay, now the catalyst that we saw here is drawn in a kind of strange way. I have this palladium, and then I've got these brackets, and then I have 4 triarylphosphines, and I'm not really showing how the bonding takes place here. And so the bonding of these metals to their ligands, those are the things that, like the phosphine, that is something now that we're going to have to take a look at in a little bit greater detail. Now, these ligands, that would be the triarylphosphine here, these ligands come in 2 types. And these are either charged or neutral. Okay, so just 2 types, and within each type, of course, is variability, but we need to distinguish ligands like the triarylphosphine, which don't bear a charge, it's a neutral molecule, from ones from other ligands where you actually do have a charge. And so let's take a look at some of these. So a very common catalyst is tetrakis triphenylphosphine palladium. And so the triphenylphosphine ligand is a very, very common one in organometallic chemistry. These form nice complex, nice stable complexes with a lot of metals. And so this is a neutral ligand. I mean, triphenylphosphine is neutral. Now, I've shown a line there indicating electron pair donation. Of course, if this is neutral and the palladium is neutral, then something has to be going on here. So we'll take a look at charges and oxidation states in a minute. Diamine dichloroplatinum is actually a cancer drug. This is one of a small number of organometallic compounds that are used in cancer chemotherapy. Almost all of them platinum right now. And it's a DNA toxin. Here you have 2 different kinds of ligands. You have ammonia, which is neutral. That's a neutral ligand. And then you have chloride, which is charged. So I have 2 charged ligands and 2 neutral ones. And so we will distinguish the neutral ones. We'll just call those L ligands. So L ligands are going to be ligands that do not have a charge. And then X ligands are going to be like chloride, where you do have a charge. Now, it follows that if you remove an L ligand, an uncharged ligand from a metal, you don't change the charge of the metal or of the ligand. So you can think of the palladium tetrakis triphenylphosphine. Now I can pull off one of those triphenylphosphines. There's no charge on the triphenylphosphine, there's no charge on the metal. I'm not changing charges when I do that. On the other hand, if I pull an X ligand off a metal, then the charge in the metal goes up by 1. So in other words, if I somehow rip off one of these chlorides, one of them only, then the platinum will have a +1 charge, okay? And so if you remove an X ligand from a metal, you remove it as X minus, and then that leaves the metal with a plus charge. So this is a fundamental difference. I mean, it should make sense to you, but it is a fundamental difference between those 2 types of ligands, and it's going to affect the mechanisms of the reactions that we're going to talk about. So here's another very common palladium compound. This is palladium acetate, this triphenylphosphine complex. So the acetoxy group here is an X-type ligand. Usually you just show that as ACO as usual. So this piece here is AC, that's the oxygen. So ACO is just this piece. And these are X ligands, these are L ligands. So if I remove one of the triphenylphosphines, no charge on palladium, no charge on the triphenylphosphine. I remove one of the acetates, negative charge on acetate, positive charge on palladium. Okay, so the difference between an X ligand and an L ligand. The X ligand has a charge, the L ligand does not. Now, this is really a bookkeeping device. Okay, so we use this, we make this distinction just because it makes it easier for us to count electrons, which is something we're going to have to do. But in fact, both the L ligands and the X ligands bond covalently to the metals. Okay, and so these are covalent type bonds. Now, there's a table in your text that lists X and L ligands, pretty complete. I don't need to go through all of it, but I'll go through a few of them. So cyanide. Cyanide turns out to be a really good ligand, again, for a lot of metals, and it invariably bonds. So you'd say that, well, okay, you know, I have an electron pair here on the carbon, an electron pair on the nitrogen. Both of these could participate in bonding. And you're right, but typically it bonds through carbon. And this is going to be an X-type ligand because why? Well, because the carbon is charged. Okay, so if I have palladium cyanide, which is a known compound, then I'll have two cyano groups on the palladium, and each one of them will be an X-type ligand. Carbon monoxide, which is a neutral molecule, is an L-type ligand. And so iron carbonyl, for example, is you can buy this stuff. Very, very stable iron 0 complex with carbonyls as these are called carbonyl ligands. These are L-type ligands. They bond through this electron pair, very similar to cyanide, except this is charged and this isn't. And these are two electron species, two electrons. So the two electrons are here, two, and those two. So these can donate to a metal, these can donate to a metal. X, L. Another common ligand is an allyl group. Now, this can be L or X. And so that makes it a little bit confusing, right? Because you think that, well, you know, which is it? Is it L? Is it X? What is it? It turns out it depends. If it is an L ligand, it's a 4-electron ligand, and that it means that it bonds actually through all 3 carbons. Or it could be an X ligand, in which case it bonds only this way through 2 carbons. And cyclopentadiene, or cyclopentadienide rather, the anion, that's a really interesting ligand. This is an L2X. So what you think of it as, think of the X ligand as being this charged carbon, and then think of these 2 pi bonds as each donating through a covalent interaction to the metal, 2 electrons. So 2 electrons from each of the pi bonds and 2 electrons from the negatively charged carbon, for a total of 6. Now, when I draw it this way, that's actually misleading because what it looks like I've got 2 different kinds of bonds from the ligand, from the cyclopentadienide, to the metal. In fact, that's not the case. In fact, that metal is equidistant from each one of these carbon atoms. And so the common CP, and by the way, the abbreviation for this is CP. So a very common organometallic complex is this one here, CP2 iron. And what does that really look like? Well, it's got a very strange structure. It's got a sandwich structure. And so I'll just put a circle in here, which is the normal way people draw this. So you have the iron, which is simultaneously bonded to each one of these carbon atoms on both rings, sandwiched between 2 cyclopentadienes. This is a brown, stable solid. In fact, there was an undergraduate experiment where we actually made that stuff. It's not hard to make. The structure is most unusual. It was postulated first by Woodward. Now, when did we talk about Woodward in Chem 272? Does anybody remember? Okay, when we talked about UV spectroscopy, I said there was something known as the Woodward rules. I said we'd talk about this guy again. This is one of the people he's known as sort of the father of modern organic chemistry. And when he proposed this structure, everyone thought he was nuts because it was so unusual. This happened, I think, in the 50s. And, they thought that, how can that possibly be? And he was vindicated, So, anyway, he was amazing. Okay, so getting back to CP ligands, these are bonded to all 5 carbon atoms, and so the distance is the same from each one of these. Now, it's a strange ligand in the sense that it's an X-type. You can think of X-type bond being distributed among 5 carbons with 20% X and 40% L. For the most part, you can ignore this. When you look at the CP ligand, you just know that it has that it has this property of bonding to the metal with all carbon atoms being equidistant. You don't really have to obsess about what percent is X and what percent is L. Okay, so take a look at that table. You'll see pretty good listing of X and L type ligands, so that you're not surprised when you see a new one. Now we're going to talk about oxidation states, and it's easy, but it's important. So the oxidation state of the metal is the charge that the metal has when you rip off all the X ligands. Okay. So we saw palladium chloride, bisphenylphosphine. These are L, these are X. So if I take off the two X ligands as chlorides, then what I'm left with is Pb plus 2. And so this is going to be known as a palladium-2 complex. And typically, the way we show that is with a Roman numeral 2, either as a superscript or in parentheses. And the reason we do that is because we don't want to show this as a charge, okay? It's an oxidation state. So this is a +2 oxidation state on palladium. Why? Well, because if the X-type ligands are ripped away with their charge, then in order for that final thing to be neutral, well, gee, the palladium is better at having a +2 charge. Simple. So now let's go back to tetrakis triphenylphosphine. So if I go to this organometallic complex, do I have any X ligands? Heck no, they're all L ligands. If I take them away, what happens to the charge of palladium? Stays the same. So this is palladium 0. So this has the same oxidation state as palladium does in a bar of palladium metal. So it's a 0 oxidation state palladium. Now, it turns out you figure, why do we make a big deal over that? Because, shoot, if you want to look at palladium chemistry, let's just take an ingot of palladium, throw it into the reaction, and see what happens. That actually will not work. The reason that these are catalytically active and that ingot of palladium is not, is because the ingot is not soluble in solvents. This stuff is. And so you can get chemistry with these kinds of complexes that you just can't get with a chunk of a metal, even though the oxidation state of the metal is the same in both. So this would be a palladium +2 complex. And the way you figure that out is by pulling off the X ligands with their charge and see what's left behind. So we've seen potassium permanganate, right? KMnO4. Well, here's MnO4, right? Permanganate. And so if I remove all of those oxygens as O2 minus, O2 minus, O2 minus, that's 8 negative charges. In order to be left with one negative charge, the manganese had to be +7. I took away all of the oxygens, which are X-type ligands. I took them away. Each one of those oxygens is -2. I'm left with a metal. That metal had to be +7 to balance it out to -1. And so this would be a +7 oxidation manganese, which still leaves the manganese, the MnO4 as -1. So your book has these rules, and I guess the rules are useful, but when I look at organometallic complexes, for some reason I don't think of the rules. I just kind of do it the way I showed you, okay? And so the rule is that if I want to look at the oxidation state of the metal, I look at the charge. In this case, the charge would have been 0. In this case, the charge would have been -1. And then I add that to the charges of all the X-type ligands, which is what we did. So that's how I figure out the oxidation state of the metal. Okay? So that's one kind of, I don't know, do we want to call that electron counting? I'm not sure we do. It is, but really it's not what we think of when we talk about electron counting. So now what we're going to do is we're going to talk about something that's a little bit more confusing, and this is the DM notation. And this is what we use to describe the number of unshared valence electrons on a metal. And these are the valence electrons that you have on the metal after you remove all the ligands with their electron pairs. Okay, so I have a complex. I remove all the ligands with electron pairs. What am I left with? Okay, that's what we're doing here. So before we look at the rules, let's just look at a couple of examples. I think it's easier to do the examples first. So here's our familiar by now, palladium 0 tetrakis triphenylphosphine. Okay? So we know that the oxidation state for that palladium is 0. We just talked about that. Now palladium has, in the neutral metal, it has 10 valence electrons. How do I know that? Periodic table, that's how. So palladium has 10 valence electrons, and and it has no X-type ligands. So if I pull away the triphenylphosphines with their electron pairs, I'm not doing anything to the electrons on the palladium, so it still has 10 electrons. So this is going to be a D10 complex. Now why D? Well, because these are electrons in d orbitals. Okay, so remember that once you get past the second row, we've got d orbitals to deal with. So this would be valence electrons in the neutral metal, that's 10, minus the charge, 0, no charge, minus the X-type ligands, and no X-type ligands. So guess what? The number of d electrons in this kind of a complex is going to be equal to the d electrons in the metal. But you expect that. It's a zero valent palladium, which is the same as the metal. And so of course that's going to be the case. Now you take this other tungsten carbonyl compound. Remember, carbon monoxide is an L-type ligand. And so carbon monoxide forms very tight complexes with a lot of metals, in this case tungsten. And so tungsten in the neutral metal has 6 valence electrons. How do I know that? Well, I'll go to the periodic table. And then I subtract from that the charge. Minus, minus, right? So minus, minus tells me that I got 2 extra electrons. These are all L ligands, so I didn't lose any when I pulled them away. That's a D8 complex. Okay, so it's got the 6 from the neutral metal and another 2. So 6, and then there had to be another 2, otherwise it would be a -2 charge. So it has to make sense to you, right? So you take the ones from the metal, you take the charge, in this case -2 charge, so hey, another 2 electrons from that, there they are. And I didn't lose any because all the ligands here are what? They're L-type ligands. So to sum up, this N value, this Dn notation, is the number of valence electrons on the metal after you take away all the ligands with their electron pairs. Now, if you're taking away L ligands, you're not taking away anything from the metal. Taking away X ligands, yes, then you're taking an electron away from the metal. Okay, so you'll do a few problems. Once you do a couple of problems, stuff becomes a lot easier. First time you see it, it looks very strange, but it actually will make sense to you if you do the problem. Okay, now, what did we say about organometallic chemistry in general? It says that, boy, this is a really rich area. There's a lot more variability. Of course, you've got all these metals, they're all different. And you've got more electrons. And also, unlike organic chemistry, which is very cut and dried and predictable, organometallic chemistry is less predictable. And you say, well, why is that? And part of the reason has to be that what we're going to talk about from now on really makes use of valence bond theory. Valence bond theory, if you go back to chapter 1 in your book, is a very crude approximation of reality. And so, as organic chemists, we're really lucky that it does such a wonderful job of predicting everything. And there's very few areas in organic chemistry that I can think of where valence bond theory really doesn't cut it. but there are a lot more in organometallic. And so we're not going to be going into that, but just so you know. Okay, so electron counting. Now, for the purposes of this course, we're going to want to know if we have an 18 or a 16 or, in some cases, a 14 electron complex. And so 18 electrons corresponds to a closed shell. That's argon, okay? And so just as we had the octet rule, which corresponds to neon, and is a stable electronic configuration of an atom, so too here, 18 electrons, there will be a special stability associated with 18 electrons. So it's a closed shell, noble gas electronic configuration. So just as we had 8 electrons, now 18. Well, what about 16? Well, 16 is 2 electrons short of 18, isn't it? So the prediction you would make is that this is going to be non-reactive. This one should be reactive. And you're right. Okay, so for main group chemistry, we wanted to know whether we had an octet, right? We did this octet rule. And, and by the way, on the exam, I saw way too many octet rule violations. That's not acceptable in Chem 272. It is surely not acceptable in Chem 273. So please, if you have any confusions about octet rule, clear them out right away. Okay? Word to the wise. So I had to say that. This prompted me. For main group chemistry, we'll be interested in the octet, but here we're going to be looking at 18, 16, 14 electrons. Okay, so we need to know how to count. Okay, so, and the reason is just this. It determines reactivity. Just as we saw in earlier discussions, that if you lack a complete octet on carbon, you expect something to happen. Here also, if you lack a closed shell, then you'll have reactivity. So the rule is, and I'll go through this briefly, but the rule is going to make sense to you. So here's the electron count. You take the valence electrons in the neutral metal, and then you take the charge, then you take the X-type ligands, and twice the L-type ligands. Now, okay, let's forget about the charge for a minute, okay? So you take the neutral metal, you count up all the electrons, right? Now, we're going to, remember when we were counting for the octet rule, we counted electrons twice. We said that, for octet rule purposes, even though you have a shared electron pair, you still count it. Well, it's sort of the same way with the L-type ligands. For the X-type ligands, you count them once, but for the L-type ligands, you count them twice. And then the charge on the metal, well, if it's a negative charge, of course you add electrons. If it's a positive charge, it means you're short electrons. That's why there's a negative sign there. So this should all make sense to you. The X-type ligands, by definition, contribute only 1 electron. That's why 1. The L-type ligands contribute 2. And the charge, if any, is going to be taken into account in the sense that I said. It's a negative charge, more electrons. Positive charge, fewer. That's why the negative charge. So let's do that. So nickel tetracarbonyl, terrible stuff. Okay, so you think, well, organometallic complex, metal. You think of nickel metal being, you think of a bar of nickel, and you think of it as being solid. Nickel tetracarbonyl is actually a gas. And it is very, very poisonous. And it releases, it causes, it's a blood poison. And so when people use this stuff in the lab, they would have, I actually saw this, when I was in grad school, we didn't have very good hoods. So, you really had to know be careful when you did this. They had a syringe loaded with BAL. BAL, I can't remember the source, it's called British anti-Lewisite. It was developed during World War I, as I recall, to counteract arsenic poisoning or something. And what it does, it will form bonds to metal, preventing the metal from forming bonds to your enzymes and killing you. And so there was a loaded syringe taped to the wall next to the hood with British anti-lewisite. So if anybody got a face full of nickel carbonyl, supposed to give themselves a quick injection. Those were the good old days. So, okay, so nickel carbonyl. So let's try to like that. So you'll never. So I can hazard a guess. You will never ever see nickel carbonyl. Now, here's another reason why you won't. Because actually you don't have to use nickel carbonyl. You can substitute, as we're going to see, L ligands quite easily. So you can form this ligand, or this organometallic complex, which is the tricarbonyl nickel triphenylphosphine. This is also an L ligand. Guess what? This is a salt ligand. It's not dangerous. It has almost the same reactivity. So no sense using gaseous nickel carbonyl anymore. Anyway, let's talk about electron counts. So nickel in the neutral metal has 10 valence electrons. How do I know that? Well, because of the periodic table. There are no charges on the nickel, so that's a 0. There are no X-type ligands either. All of these are L-type ligands. So I've got 10 electrons from here, and each one of these ligands contributes 2 electrons because it's an L-type ligand. 2 times 4, 8. 10 plus 8 is 18. So that's a stable stable 18 electron compound. Okay? So how did I know that? No charges, no X-type ligands, but it has 8 electrons from the 4 L-type ligands and 10 from the neutral metal. Okay, now palladium chloride bistriphenylphosphine, which is a +2, so palladium is in its +2 oxidation state. By the way, nickel here is what? 0 oxidation state. Here it's +2, but no charge. So the electron count for palladium is also 10. Palladium is right below nickel on the periodic table. So if nickel is 10, this is 10. 10 plus 4 is what? 14. 2 electrons from each of the triphenylphosphine, but only 1 electron from each of the chlorines. Because why? Because chloride is an X-type ligand contributing 1 electron each. So add them all up, this is a 16 electron complex. And so the prediction would be that this is probably reactive, and it is. Okay, so to sum up, 18 electron complexes, very stable. Very stable because they have the same number of valence electrons as argon. So it's a closed shell configuration, stability associated with the noble gas closed shell configuration. So it's the same thing really that we saw with the octet rule, except as we go down the periodic table, there's more than 8 electrons, and so we have this 18 electron. So in the case of main group compounds, we used hybridization to explain the 8 electron rule. Remember when we looked at, way back when, in Chem 272, we looked at carbon, and we said that, well, you know, if we look at carbon, really, that means that methane should be CH2, because I only have two electrons in a unfilled shell. But everybody knows that methane is CH4. And so why would then methane be CH4? And then we figured out that, well, it's because in methane, carbon is what? It's sp3 hybridized, so it can form 4 bonds. And then the question was, well, why does carbon want to form 4 bonds? Because when it forms 4 bonds, it has 2 times 4, 8 electrons for the octet rule, and it satisfies the octet rule. Remember that, right? So with carbon, we rehybridized it. We made it, for methane, we made it sp3 hybridized. Well, we didn't make it. I mean, it just is. We rationalized it. And we said that the reason it is sp3 hybridized is because that allows it to fulfill the octet rule. Okay, so now we have, not the octet rule, we have the 18 electron rule. And so, you guessed it, the compounds are going to hybridize in such a way as to satisfy either an 18 electron or a 16 electron rule. And so, just as we had hybridization to satisfy the octet rule, we're going to see something that is more complicated but completely analogous to the 18 electron rule. Okay. So we're going to illustrate that with cobalt, hexacyanyl cobalt. So cyanide, like carbon monoxide, forms strong complexes with a lot of metals. In this case, and by the way, cyanide is not like carbon monoxide because cyanide is an X-type ligand, right? Carbon monoxide is L-type. X-type ligand with cobalt, and now we have this negatively charged complex. Okay, so let's take a look at this and figure out, let's do the first thing, oxidation state of cobalt. Okay, so let's hide everything. What is the oxidation state of cobalt? Well, we don't need the periodic table for this. Okay, so the oxidation state of cobalt is going to be whatever charge cobalt has after I pull away all of the X-type ligands. Well, I got 6 cyanides, right? Each one of those has a negative charge. Okay, so I've got 6 negative charges. And now what must cobalt be? What oxidation state must cobalt be in order to still end up with -3? It's got to be +3, right? Okay, so the oxidation state is going to be X-type ligands plus the charge. 6 plus -3, because minus charge, is going to be +3. So this is a cobalt +3. Okay, so that was easy. Now, electron count. So cobalt has 9 valence electrons in the neutral metal. How do I know that? I know that by looking at the periodic table. Okay, so iron is 8, cobalt is 9, nickel is 10. Okay? And so that you probably will remember at some point. You don't have to, periodic table is here. Then I add the charge, and I have to add the charge with a negative sign, right? Because if I have a negative sign here, that means I got 3 extra electrons. So -3 adds 3 electrons. And then I take 1 electron each from all of the X ligands, and I don't have any L ligands. So when I put all of this together, it's an 18 electron beast. Okay, so 18 electrons. Guess what? It's a closed shell. Okay? Well, that's why I picked it, right? We picked it because it is a closed shell. The N count is given, this is a D6 complex. So you can go through and figure out, the N electrons, you add the charge, and then here, instead of adding, you subtract out the 1 electron for each of the cyanides. This is a D6 complex, which means what? Which means that we have 6 electrons in the cobalt that we need to figure out what to do with. So now there's a strange thing that happens with the energy levels, and that is that the 3d orbitals are lower in energy than the d orbitals are lower. That's not a strange thing. 3d are lower than 4s and 4p. You have 5 of these, and S you only have 1, P 3, just as we saw before. So I have all of these orbitals are available to cobalt. But remember that there are 5 of these. Now, how many electrons do we need to put in there? 6, right? So what does Hund's rule tell us? Remember, Hund's rule tells you that you think of the orbitals being pigeonholes. And so we throw electrons into each one of those pigeonholes. But the way you do it is you put 1 electron here, and then you don't put another one in here because those 2 electrons have negative charges, and they'll repel. So the next one goes in here, and the next one goes in here, and the next one here and here. And then the 6th one, well, run out of orbitals, it's going to go in there. Okay? So we're going to do that right here. So we populate, according to Hund's rule, we populate the orbitals of lowest energy first, 1 electron at a time, right? So that's what we did. We have 6d electrons, so there it is, 3d6, it's a d6 complex. These are empty. I put two, or I had to put two in here because once I filled all 5 and I had one left over, there it is. So these are all singly occupied because of Hund's rule. So that's how we did it with carbon too. What did we do next with carbon? Well, we took all those singly occupied orbitals and we hybridized them. Oh well, we bunched them up and then the rest of them we hybridized. So we then do something that costs us energy. We bunch them up. So instead of having singly occupied orbitals here, I've got 3 doubly occupied. That costs me energy. So pairing up the electrons into these orbitals, that costs energy. But we get that energy back when we take all these red orbitals that are unoccupied and hybridize them. So 1, 2, 3, 4, 5, 6. I have 2 Ds, 1 S, and 3 Ps. And so the hybrids are going to be 2 Ds, 1 S, and 3 Ps, D2ST3. Now, when we did the hybridization with carbon, we specified that it was a 2 sp3 because both the S and the P orbitals that we hybridized were at the quantum level 2. But here, notice what we're doing. We're hybridizing orbitals that are in different quantum levels, 3 and 4. And so there's no 3 or 4 here. It's just that. Okay. So we have 1, 2, 3, 4, 5, 6 empty orbitals. 1, 2, 3, 4, 5, 6 hybrids. And guess what? There go the 2 electrons from each of the 6 cyanides. And so the green electrons come from cyanide, the red electrons come from the cobalt, and now we have a closed shell. And this is the closed shell for a 18 electron complex. Now, so this is the closed shell. These are the valence orbitals. So these are valence orbitals. They have they're all completely filled. Now these are all of identical energy. The way we made these all have the same energy. So I got, now, unlike sp3 carbon, where I had 4 orbitals of identical energy, here I've got, how many? 6 of identical energy. And so if I'm going to get 6 orbitals as far away from each other, then what I'm going to end up with is an octahedral complex. Now I'll draw that out for you, a little different. Take a look at that. I haven't shown the charge here. So what I'm going to have, think of this. Think of an octahedron that looks like this. Okay, so the metal is right here. There's the metal, and here are the ligands. The ligands are right there. So the 1, 2, 3, 4, 5, 6 ligands are equidistant to that metal. So it's kind of a square pyramid on top of another square, but an inverted square pyramid. And so that's the shape of the cobalt hexacyanocobalt anion. So let's go through that again. So we had 6 electrons from the metal, from the cobalt. And the way we knew that was just by counting up the electrons that the metal had. And according to Hund's rule, we fill up the orbitals this way, and then to hybridize to form the hybrid, you bunch these up. That leaves us with 6 empty orbitals. 2 are D, 1s, and 3p. So we end up with a D2ST3 hybrid, 6 of them. Each one of these can accept 2 electrons, 1 electron pair from each of the cyanides. These are all of equal energy. So if they're of equal energy, that means that there's no difference between the cyanides. And so that means that the cyanides all have to be equidistant to the cobalt. And that means that the way you do that is with a octahedral complex. So the cyanide is equidistant also from each of the from each cyanide is equidistant to cobalt. So why bother to go through, in other words, why does cobalt do this? Well, cobalt doesn't do this, it's just the way nature is. So cobalt didn't make a conscious decision to do this, presumably. The reason is that the same reason everything happens, right? This happens because it's lower in energy than the alternative. And so why should this be lower in energy? Well, the same reason we've seen time and time again, because the hybrids form stronger bonds. And so you get stronger, tighter bonding when you have the hybrids, and that's why it happens. So all of this is our explanation of reality, which is that. Okay? So just remember that. You know, we go through this explanation, but the reality is given to us. And what we do is we try to explain it in a way that is self-consistent. We do a pretty good job, I have to say. This argument, even though it makes use of valence bond theory, actually has predictive power. So any one of these arguments that we make is going to be valuable only so far as it allows us to predict things. It doesn't allow us to predict things, it's kind of useless. But it does allow us to predict things, that's why we go through it. So, just to sum up here, so the 18 electron rule results, as you can see, from this rehybridization and repopulation of all of the orbitals so that you achieve a noble gas configuration. In this case, the noble gas is argon, right? And so, just as we saw with the 8 electron rule, you end up with a different noble gas configuration here because you have more electrons. Now, with 16 electron complexes, you know that we're going to have a different hybridization scheme. Okay, so 16 electron complexes are going to be pretty different. They're not going to be octahedral for one thing. And so now we need to take a look at a 16 electron metal complex and try to figure out what that's going to look like. So the 16 electron complex we're going to pick is this platinum, the anti-cancer drug. By the way, the trade name for this is cisplatinum. Why cis? Cisplatinum. Yeah, because the two chlorines are on the same side. This is, by the way, square planar. All of those atoms are on the plane. So what that means is that there's actually the possibility of a transplatinum too, right? That would be this complex. And so this would be an isomer of the cancer drug with the two chlorines on opposite sides of the metal. But in fact, they are on the same side. Okay, so that's why that goes by the name of cisplatinum. Okay, this is a D8 complex. Why is that? Well, because platinum, which is underneath palladium, also has 10 electrons in the neutral metal. There's no charge. I have two X-type ligands, they're chlorines, so I pull off one electron from each. And these are L-type, so these don't count. So it's 8. It's a D8 complex. So now I'm down one in the periodic table. So I'm at the quantum level 5 and 6, not 3 and 4 as we had before. So 5 and 6. And so if I put the 8 electrons, I'm skipping a step here, right? Because Hund's rule would tell you to put them in the electron singly occupied. So I should have 2 singly occupied orbitals. I've already bunched them up. That leaves me 1, 2, 3, 4, 5 orbitals that I can hybridize. But actually, I hybridize these 4 and leave one empty. So one of the 6 p's stays empty. The other 4, which is a D, an S, and 2 of the p's, a D, an S, and 2 of the p's get hybridized. And 2 electrons go into each of the hybrids. 2 from this nitrogen, 2 from that nitrogen, 2 from this chlorine, 2 from that chlorine. So the green electrons come from the ligands, the red electrons from the metal. And so this is a little bit different hybridization scheme. It results in a square planar complex, which means that Chlorine, chlorine, nitrogen, nitrogen, and platinum are all in the plane, and the empty orbital is above and below the plane of the metal. And so this would be the hybridization scheme for a 16 electron species. So it looks very much like what we saw for carbon, only different orbitals and more electrons. And so since most of you probably have not read this from the looks on their faces, it would be a really good idea before Friday to read chapter 18. Okay? So I'll see you all on Friday.